Good morning, students. Welcome back to the lecture number 12 on basic properties of fluid mechanics. Myself, Praveen Yadav, assistant professor in mechanical engineering department. And now today we are going to discuss about the numerical problems on the basic properties which we have studied in the last lecture. So in last lecture, we have studied about viscosity, compressibility, surface tension, and capillarity action. Over that, numericals on viscosity we have already conducted in lecture number 10. Now today we will focus more on compressibility, surface tension, and capillary action. So just for revision purpose, on the numericals on viscosity we have taken, know that shear stress tau can be given as mu into du by dy, where mu is nothing but viscosity. Then kinematic viscosity nu is equals to mu by rho. So, and the specific gravity of fluid S can be given as specific weight of given fluid divided by specific weight of standard fluid. So using these formulas we are going to solve the numericals on viscosity. Again, a specific gravity of fluid S is nothing but density of given fluid divided by density of water. So first one problem is find the kinematic viscosity of an oil having density of 981 kg per meter cube. The shear stress at a point in oil is 0.2452 Newton per meter square and velocity gradient at that point is 2 per second. So this is the problem. Now from the problem itself, it comes to know that oil is less denser than the water, that is standard fluid which is going to be provided than the water. So oil having density is equals to 981 and shear stress at the point of oil is 0.2452 Newton per meter square. So based on this, initially write the given mass density rho is nothing but 981 kg per meter cube, shear stress tau is equals to 0.2452 Newton per meter square, and velocity gradient it is given as a 0.2 per second. Okay, so putting these values, shear stress can be given as tau is equals to mu into du by dy. So from this formula, mu can be calculated as mu is equals to 0.2452 divided by 0.2. So kinematic viscosity of viscosity at here is equals to 1.226 Newton second per meter square. Now the kinematic viscosity nu can be given as mu by rho. So mu is equals to 1.226 divided by rho is nothing but 981. So the kinematic viscosity is 0.125 into 10 to the power minus 2 meter square per second. Okay. Now consider the another problem. Determine the specific gravity of fluid having viscosity 0.05 poise and kinematic viscosity 0.035 Stokes. Now in a previous lecture only we have discussed about unit conversion of poise and Stokes. Now here they have given the viscosity in a poise as well as kinematic viscosity in a Stokes. So initially convert the viscosity into Newton second per meter square. So we know that 10 poise is nothing but 1 Newton second per meter square. So mu can be converted as 0.05 poise is nothing but 0.05 divided by 10, that is 0.005 Newton second per meter square. And the kinematic viscosity it is given is equals to 0.035 Stokes. So it is nothing but 0.035 centimeter square per second. So to convert it into meter per second square, it is required to multiply by 10 to the power minus 4. So it is equals to 0.035 into 10 to the power minus 4 meter square per second. That is the kinematic viscosity. So, but we know that kinematic viscosity nu is equals to mu divided by rho. So from that density rho can be calculated. So put out the values of mu and calculate the value of rho. So rho value can be given as 1428.5 kg per meter cube, 1428.5 kg per meter cube. Now this according to this density, we know that specific gravity of liquid can be given as density of liquid divided by density of standard fluid, that is water. Now density of water is 1428.5 kg per meter cube, and density of water, it is standard, it is equals to 1000 kg per meter cube. So it is divided by 1000, so answer is equals to 1.428. So the specific gravity of liquid or fluid which has to be used is 1.428. What is the unit for specific gravity? It is unitless because it is the ratio of two densities. So the output should be given in the format of unitless quantity. Okay. Now numericals on bulk modulus. Now we have discussed about what is bulk modulus. It is the ratio of change in pressure with respect to ratio of change in velocity with respect to original velocity. And we know that reciprocal of bulk modulus is nothing but compressibility. Reciprocal of bulk modulus is nothing but compressibility. So we'll take first problem. When the pressure of liquid is increased from 3.5 meganewton per meter square to 6.5 meganewton per meter square, its volume is found to decrease by 0.08%. What is bulk modulus velocity of the liquid? Now in this problem we have given the change in pressure. The pressure of liquid increases from 3.5 to 6.5, and change in volume also. The change in volume is 0.08%. Now the change in volume is given in terms of percent. So we have to calculate the bulk modulus of velocity for the given liquid. So initial pressure is nothing but 3.5 meganewton per meter square. Final pressure is equals to 6.5 meganewton per meter square. So change in pressure is nothing but the difference between two is 3 meganewton per meter square, that is 3 into 10 to the power 6 newton per meter square. Okay. Now decrease in volume is 0.08%. That is decrease in volume to the original volume percentage is 0.08%. That is, it is the ratio of dV by V in percentage format. So dV by V can be given as 0.08 divided by 100. So multiplying it, it will get 0.08 into 10 to the power minus 2. Okay. Now from the above entities, bulk modulus K can be given as, how to calculate K? K is nothing but dP divided by dV minus V. And here, since volume is decreases, the signature, the sign should be a negative. So minus dP divided by dV by V. So it's nothing but 3 into 10 to the power 6 divided by minus 0.08 into 10 to the power minus 2. So K can be given as minus 3.75 into 10 to the power minus 9 Newton per meter square. So the bulk modulus of velocity for the liquid is minus 3.75 into 10 to the power minus 9 Newton per meter square. Now suppose from the same formula, if you want to calculate the compressibility, then how would you calculate? It is nothing but the reciprocal of bulk modulus. So reciprocal of bulk modulus can be given as 1 by K, and it is equals to 1 upon minus 3.75 into 10 to the power 9. So that is called as a compressibility. This indicates that from this given formula, if you calculate the compressibility, it comes as equals to 1 divided by 3.75 into 10 to the power 9. So it is approximately equals to 3 into 10 to the power minus 9. So from this it is here it is clear that the compressibility ratio for this liquid is very less. So liquid is uncompressible or not compressible. This is about bulk modulus. We have taken one simple example. Now take examples on numerical on surface tension. For surface tension purpose, we have calculate surface tension values by considering the shape of that fluid droplet. So for water droplet purpose, P can be given as 4 sigma divided by D. For soap bubble purpose, P can be given as P is equals to 8 sigma by D. And for liquid jet purpose, P can be given as P is equals to 2 sigma by D. For that purpose, we have taken the help of equilibrium equation. If you have remembered, that we have considered that the water droplet is in a spherical form. We have cut it from the center over its periphery, sigma with the stress acting towards the left hand side, towards the right hand side, and the fluid inside it consisting pressure P acting opposite to that, and that P is acting over the peripheral pi by 4 d square. So by solving that, we have got P is equals to 4 sigma divided by d. For soap bubble purpose, since the bubble inside it also and from outside also it consists environmental air as an media, so it undergoes two directional stresses. That's why P value increases from 4 by 6 by d to 8 by 6 to 8, that is it will get doubled. And for liquid jet purpose, we have considered it as a cylinder. Jet is considered as a cylinder. So by taking the cut section of cylinder along its length to the both ends, sigma with the stress acting over the cylinder and over the cross sectional area, pressure P will be acting, and from that we have calculated P is equals to 2 times sigma divided by d. Okay, so by using these formulas we are going to solve the problem. And the problem is the pressure outside the droplet of water diameter 0.04 mm is 10.31 Newton per centimeter square. That is called as an atmospheric pressure. Then calculate pressure within the droplet if surface tension is given as 0.075 Newton meter of water. Now see here, sigma it is given as 0.075 Newton per meter. Diameter of droplet it is given as 0.04 mm. That is requires to convert into meter by multiplying it into 10 to power minus 3. Now surface outside the droplet is equals to 10.32 Newton per centimeter square. So again it is requires to convert into meter, that is 10.32 into 10 to power 4 Newton per meter square. Now we have to find out pressure within the droplet itself. Now the pressure inside the droplet increases of outside pressure is given by equation P is equals to 4 sigma by d. So pressure P can be given as 4 into 0.075 the surface tension divided by the diameter of peripheral, and the pressure is equals to 7250 Newton per meter square. Now in this problem the interesting thing is that there is no any affection of pressure from the outside, because here it is clearly mentioned that droplet of water. Suppose it is considered here explained as a droplet of air bubble, then it is required to be the considered pressure at atmospheric pressure or pressure from the outside. So that point you always remember it. Okay. Now pressure inside the droplet is 7250 Newton per meter square. Pressure outside the droplet is 10.32 into 10 to the power 4 Newton per meter square. So pressure within the droplet is nothing but the pressure inside the droplet plus pressure outside the droplet. So it is equals to the summation of both. It is gives the summation of both. Okay. Now find the surface tension in soap bubble of 40 mm diameter when the inside pressure is 2.5 Newton per meter square above atmospheric pressure. Now this is the problem of soap bubble. Surface tension in a soap bubble of 40 mm diameter, that is it is required to be converted into meter when the inside pressure is 2.5 Newton meter square, that is P also has been given at here. So D has been given, P has been given. So for soap bubble we know that P is equals to 8 times sigma divided by D. So surface tension sigma can be given as sigma is equals to 2.5 into 40 into 10 to the power minus 3 divided by 8. So sigma can be given as 0.0125 Newton per meter. Now we'll move further for the capillarity actions. We know that capillarity effect we have discussed at the last of the lecture, yesterday's lecture. So capillarity effect can be given as H is equals to 4 times sigma divided into cos theta divided by P G into D, where sigma is nothing but surface tension and theta is nothing but angle of contact between the liquid and glass. Now value of theta between water and clean glass tube is approximately equals to 0. That is we are considering that water level is flat inside the capillary action. The rise of water is given by value of theta for mercury in glass tube is 128 degree. That is we have considered. So this is we have discussed in the last lecture how we are going to calculate the angle of contact. Now consider the problem. Calculate the capillarity rise in a glass tube of 2.5 mm diameter when immersed vertically in a water and mercury. Consider surface tension sigma is equals to 0.0725 Newton per meter for water and sigma is equals to 0.52 Newton meter for mercury in a contact with air. The specific gravity for mercury is given as 13.6 and angle of contact is 130 degree. Now here theta value is given as equals to 130 degree. Now here we have to calculate rise in water as well as rise in mercury. Okay. For in a glass tube having diameter of 2.5 mm, that is very small diameter. Sigma has been given for water is equals to 0.0725 Newton per meter and for mercury it is 0.52 Newton per meter. Now from this we have to calculate capillarity rise. Again, the interesting thing is that specific gravity for mercury is given as 13.6. Why not given to water? Think on this, because specific gravity is nothing but the density of fluid divided by density of standard fluid, and standard fluid we are considering as the water. So specific gravity of mercury is 13.6. For water it is equals to 1 because it is the ratio of density of water to the density of water. Okay. Now here in a given diameter of tube D is equals to 2.5 mm, so it converted into meter. Surface tension sigma is equals to 0.0725 Newton per meter. Sigma for mercury is 0.52 Newton per meter and specific gravity of mercury is equals to 13.6. Therefore density can be given as 13.6 into 1000 kg per meter cube. So capillarity rise of water at theta is equals to 0. H can be given as 4 times sigma divided by rho g d. So it is 4 into 0.0725 divided by 1000 into 9.81 into 2.5 into 10 to the power minus 3. So it is equals to 0.0118 meter. So rise in water in a capillary is equals to 1.18 mm. Now for mercury, angle of contact between mercury and glass is equals to 130 degree. So H can be given as 4 times sigma cos theta divided by rho g d. So 4 into 0.52 into cos of 130 divided by 13.6 into 1000 into 9.81 into 2.5 into 10 to the power minus 3. Now here how 1000 comes? 13.6 into 1000 because we have calculated the density of mercury, and density of mercury is nothing but specific gravity into density of standard fluid water as 1000. Okay, so it is equals to minus 0.004 meter. Here minus sign indicates that fall in mercury level in a capillary, and it is nothing but the fall is up to 0.4 centimeter. Okay, now I think this is the last problem. Find out the minimum size of glass tube that can be used to measure water level if the capillary rise in the tube is to be restricted to 2 mm. Consider surface tension of water in contact with air at 0.073575 Newton meter. Now here the problem is in a reverse direction. Already capillarity rise is restricted by 2 mm, which is given as H is equals to 2 into 10 to the power minus 3 meter, and surface tension is given is equals to 0.73575 Newton meter. Now consider diameter of tube D is equals to diameter of tube is equals to D in meter, and the angle theta of water is equals to 0 because for water purpose the standard angle of immersion is 0, and we know that density of water rho is equals to 1000 kg per meter cube. Now we know that H is equals to 4 times sigma divided by rho g d. Now put out the all values of H, sigma, rho and g and calculate the value of D. So D can be given as D is equals to 4 into 0.073575, that is 4 sigma divided by rho g into H. So rho is 1000, g is 9.81 and H is equals to 2 into 10 to the power minus 3. So from this D can be given as 1.5 centimeter. Thus, the minimum diameter of tube should be 1.5 centimeter. Now, calculate the capillarity effect in millimeters. A glass tube of 4 mm diameter when immersed in a water and mercury. The temperature of liquid is 20 degrees Celsius and value of surface tension for water and mercury at 20 degrees Celsius in contact with air is given as 0.73575 and 0.51 Newton meter respectively. Find the angle of contact for water is 0 and for mercury is 130 degree. The specific weight of water is 9790 Newton per meter square. Now here see, instead of taken specific weight of water has been specially given 9790 Newton per meter square, and specific gravity for mercury is equals to 13.6. So diameter D is equals to, converted to meter. The capillary rise can be given as 4 times sigma cos theta divided by rho JD. Sigma is equals to surface tension, theta is equals to angle of contact, and rho is equal to density. So sigma here it is given as 0.073575, theta is equals to 0, and mercury for it is 13.6. Now capillarity effect for water, sigma has been given, theta has been given, rho has been given. At 20 degrees Celsius, value of rho is equals to 998 kg per meters cube. It is given. So from that, calculate the value of H. So H can be given as 4 into 0.73575 into cos of 0 divided by 998 into 9.81 into 4 into 10 to the power minus 3. So H can be given as 7.51 into 10 to the power minus 3 meter, or 7.51 mm. So rise in water level is equal to 7.51 mm for water. Now for mercury purpose, we know that H is equals to 4.6 cos theta divided by root GD. Now here specific gravity is 13.6. So density can be given as density of mercury is equal to 13.6 into density of water. So it is 13.6 into, now standard density of water is considered as 1000, so don't take 998, instead of that take directly 1000. So density of mercury is equals to 13600 kg per meter cube. Now we know that H is equals to 4 times sigma divided by cos theta divided by rho GD. H, so we have to calculate sigma for mercury, it is given 50.51 Newton meter. Theta is nothing but 130 degree, so cos of 130 degree divided by rho 13.6 into 1000, that is 13.6 into 10 to the power 3 into G 9.81, and D is given as 4 into 10 to the power minus 3. So from that H is nothing but minus 2.46 into 10 to the power minus 3. So negative sign again here indicates depreciation, and the total rise in water level, decrease in mercury level is nothing but 2.46 mm. So these are some problems we have discussed related with the capillary action, surface tension, kinematic viscosity, and etc. Now we are moving towards the last point of this chapter, that is measurement of pressure. That part we are going to see in next lecture. Thank you very much.